Okay guys, question 9 here is about electromagnetic induction. We have a coil rotating at a constant frequency in a uniform magnetic field. It's the usual situation, and we have to explain how an EMF is induced in the coil. So of course we know as the coil rotates, we know that the magnetic flux through the coil changes, and that is why we get an induced EMF. So as the coil rotates, the magnetic flux through the coil changes with time. And we know whenever you have a changing flux, you have an induced EMF. So let's just mention that that is Faraday's law. So Faraday's law says that a changing flux induces an EMF in the coil. Of course, Faraday's law says actually something a little bit more than that. It does say that the induced EMF is the rate of change of flux through the coil. So let's just throw that in there as well. Okay. Then here we have the output voltage, and it's this sinusoidal variation. And it asks us for the average power output of the, well, it tells us what the average power output of the generator is. So that's P bar in the formula booklet. Calculate the root mean square value of the current, right? The RMS, IRMS. Okay. Well, if we look in the formula booklet, you can see that the average power is half times the peak power, which is peak current and peak EMF. We can read off the peak EMF from the graph. That's 25,000 volts. 25, 10 to the 3 volts, and we are told that that average power is 8.5, 10 to the 5. Okay, so from that we can get the peak current, comes out as exactly 68 ampere, and when I have the peak current, we can always find the RMS. Whenever you have a peak value, you can find the RMS value. That's just the peak divided by root 2. Gives us around 48 amps. Okay. Don't forget that the average power can also be worked out as just the product of the RMS current and the RMS voltage. That's sometimes useful to know. Okay. Then here we have the voltage power is stepped up before the transmission, and we do that of course to reduce the current in the transmission line so that we reduce the power loss due to the resistance in the transmission cables. They ask about that a lot on the exam questions, so make sure you understand that. Estimate the factor by which the voltage has to be stepped up in order to reduce power loss by a factor of 250. So we have to remember here, I'm just going to write it down here, that power is proportional, the power loss in the cables, right, is proportional to I squared. P equals Ri squared. So that means that, well, the ratio of the new power to the old power equals to the ratio the new current squared to the old current squared. Now we want the power, the new power, to be 250 times smaller than the old power. So the ratio between the powers is 1 over 250. From this we can get that the new current has to be 1 over root 250 times the old current. Okay, so the new current has to be this time smaller than the old current, and because the voltage and the current are inversely proportional, remember that, then we basically need to step up the voltage by a factor 250. If we're lowering the current by a factor of root 250, then we need to step up the voltage by a factor of root 250. like that. Okay, so that's basically the answer. And the factor by which the voltage has to be stepped up. So the factor is root 250, and I would have thought of just leaving it like that, but the IB, they're sort of a little bit silly sometimes, that it seems like they won't give you the point if you don't actually work it out as a rounded quantity. You know, 2 sig figs, you can see they're giving us this to 2 sig figs. So, you know, try, I know that if you're good at math, you're used to leaving results as exactly as possible. But on these physics papers, they really like you to sort of calculate exact values as rounded off values. So let's just work this out as approximately 16 to 2 sig figs. Okay. Good. Last one, the frequency of the generator is doubled. No other changes made, and they're talking about the, you know, the angular frequency. Of course, it can also just be the normal frequency, but we're thinking, you know, the most convenient thing is probably to think of this as the angular frequency. Doesn't really matter. Draw on the axis the variation with time of the voltage output of the generator. Okay, well, it's again a very standard question that you have to sort of remember that, say this is a nice sinusoidal variation of our voltage. Maybe you can remember that the peak voltage is actually also given by omega AB. So that's something that one can work out. So you can see that the voltage is directly proportional to the angular frequency. If we double the frequency, then the peak voltage is going to double. That's one thing that's important to know. But of course, the period is also going to halve, because we know the period is inversely proportional to angular frequency. So you have to just draw this nicely, where the period is now 5. Sorry, it was 20 before. Now it's going to be 10. Right, so we're going to have one full oscillation in 10 milliseconds, and it's going to reach the peak, which is 50 now, after 5 milliseconds. Right, so sorry, what am I doing? Half of 5 is 2.5. So it's sort of roughly like that, and then it's going to be 7.5 where it reaches the minimum. So it's going to be something like this. Let's see if I can draw this nicely. Whoops, that wasn't too nice. Let me try again. You want to really try and draw these curves as accurately as possible, okay? And then one more. So now it's like this. So what's that? 10 plus 2.5, 12.5, and then 17.5. Something like this. Try your best, you know, do this with a pencil first until you get a really nice curve, and then you can maybe trace it over with a pen. Okay, there you go.